So the title of this talk is the mass contradiction in Einstein's relativity with its connection to Newton. And I'm just concentrating on the maths bit from the video, Introduction to Relativity, at this address. It's by a lecture by Dr. Mike Young, and I've got a picture of him. There he is, Dr. Mike Young, and here's a website on him. There he is at the top. He's a professor of physics, and he's at Santa Barbara City College, and he's given a talk on relativity here, and it's basically going to be highly messed up, really. So let's get to that next bit. He's going to manipulate the maths and make a transition from Newton to Einstein. There is a lot I can complain about, but I want to just concentrate on the connection between how Newton deals with time in this maths with how Einstein deals with time. Because Dr. Mike Young is going to contradict himself, and he has a different connection between how Newton deals with time with how Einstein deals with time. We have two different bits of maths contradicting themselves, and this is presented as Einstein's relativity. Einstein's relativity is nonsense, its maths is messed up, and what we have here, which I'm going to highlight, is just one example of how that maths is messed up. It has connection between Newton and Einstein in the maths which is going to be presented, and it's going to then be messed up because there's going to be a different connection made as well. It's going to be a contradiction. So Dr. Mike Young is going to go through a thought experiment, and that thought experiment will start based upon Newtonian physics, and the maths from that is going to be consistent with Newtonian physics, and then he's going to make a transition to deal with the time in that the way that Einstein deals with time. And so that will be the connection between how Einstein deals with time and how Newton deals with time. And he's then going to carry on to talk a bit more, and then he's going to contradict himself, and he's going to present a different connection between Einstein's time and Newton's time, and that is messing the maths up. The maths is just then nonsense. That is presented as Einstein's relativity. It is basically unrecoverable. That is messed up. You have maths which is nonsense as Einstein's relativity, and so say if you're going to do an experiment then to test that, well, you cannot really test nonsense, because with nonsense anything is true, and that's basically what the problem is. When you've got this contradiction between the two different ways that Einstein time is connected to Newton's time, that is a contradiction, and it's nonsense. It has messed it up. It's like saying 1 equals 2, and it's or not only that, but 1 equals 1 sometimes, but then sometimes 1 equals 2, and that is nonsense. When you have mathematical nonsense like that, there is nothing then recoverable from the theory. It's no longer testable. A theory has to make sense for it to be testable. You cannot test nonsense. If you have nonsense, all it means, and you put that to the test, then the test is just nonsense as well. You cannot confirm nonsense or disprove nonsense. It's just nonsense. There is nothing you can do with it. So let's get down to this thought experiment. Here we go.
And so as these trains would come in and out, he began to think along those lines and say, okay, what's going on in this train? So let's do this. Let's put somebody in the train for a moment. And let's take two views. One view being in the train, one being out of the train. For discussion, I'll say I'm in the train, you're out of the train. All right? Now, if I'm in the train, and for simplicity, let's say I take a ball and I throw the ball straight up. just to make some round numbers, let's just say I throw it up at 30. Huh? Well, that's what I was basing on the units. I was going to say 30 meters per second, but, well, that'd be about 66. I don't know. Yeah, I might still be able to throw a ball at 66. But, okay, would you feel better if it's miles per hour? I can do that. 30 miles an hour. All right? I just been wanting to stay away from the English system, but all right. But nonetheless, I'll do the 30. And then the train, let's say the train is chugging along here at 40 miles an hour. And I just wanted to pick some nice even numbers so we could do this kind of quickly in our head. I would see the ball go straight up at 30. Fair enough? What would you see? Yeah, you would probably see this parabola in its shape. But let's just talk about its speed right here. What would you say its speed is? 50. How'd you get 50? Right, we went back to physics 121, right? You said, well, this is Pythagorean theorem, right? If I have a horizontal leg that is 40, and I have a vertical leg that's 30, I would add the two together, and I'd get 50. And so basically what you did is this. You said, I'll take the horizontal speed, I will combine it with the vertical speed, and I'll get the total speed. Fair enough? But why did you do Pythagorean theorem?
So basically, it is sense at the moment, but you've got to provide that you're dealing with an idealised case here. You're ignoring things like air resistance and gravity and so forth to make it straight line motion for that Pythagorean triangle. So far it's sensible.
Because I told you how to do that in Physics 121? Yeah. Well, good thing Einstein went a step further. Why did I tell you that it would work that way? What was the reasoning behind? And this is Einstein's brilliance. He says, well, wait a minute, let's see. I guess it would be something like this. What if we take a look from the inside? The inside might look something like that. We may say that it goes up a height h, as it maybe goes up to the top. And let me just do this without gravity, just to kind of keep it simple. Obviously, there would be gravity slowing it down here, but just to kind of get...
So we're making that idealisation of no gravity. So you've got to bear in mind that idealisations are being made.
To the basic idea here is we would go up and say, okay, we're going to go a height h. And you probably would say then, okay, this is the vertical speed, this is the time, this equals h. Fair enough? If it was outside, or if somebody was watching from the outside, so you guys are watching from the outside, you would have taken this ball and you would have said, well, it's really doing something like that, right? It's off at an angle. And you may say that angle then is theta. But since it's going to go up and hit the roof, then what I would want then is to know what is the vertical speed. So you might take the speed, multiply it by sine of theta, multiply by time, and get h, right? And in fact, maybe I should just, for clarity, not call this the y, but say this is the speed I would observe on the inside, so I'll put inside. This is the speed you would observe on the outside. Okay. If I, just for the sake of discussion, replace sine theta with the square root of 1 minus cosine squared theta, t equals h. And I know at this point you're going, why would you do that? It's like
that is an equation from trigonometry. So
making it harder. Okay, but the reason for that is, what would cosine of theta represent here? Yeah, the x direction. So this would be the velocity then of this train divided by v. Fair enough? And I'll say v on the outside. So what I would have, and maybe I'll square everything first so that I can get rid of this crazy square root. So I'll have velocity on the outside squared. I'll have 1 minus, and in place of cosine, I've got velocity then of the train divided by the velocity on the outside. Those are squared, multiplied by time squared is equal to h squared. Fair enough? All right, well, let's keep going, because even though we didn't do this directly in Physics 121, we really did do it indirectly. We then said, well, here's h, and here's an h. Let me square that. So this would be velocity on the inside squared, time squared is equal to h squared. So when I do this substitution, I get velocity on the outside.
So those two equations he's equating, you've got h squared in both of them, so you can equate those two equations. That's what he's writing out now.
Squared, and I'll just do the distributive property. Here would be minus the velocity squared of the train. Each of those multiplied by time squared would equal to velocity on the inside squared times the time squared. Are you beginning to see how we got it now?
So what we got here is still maths consistent within Newtonian physics. So this is what you should bear in mind. So far we've got Newtonian physics. This thought experiment is just using Newtonian physics so far.
Right? I mean, isn't that going to come out to Pythagorean's theorem? I mean, isn't there a time on both sides? And so that time would cancel with that time, right? That is the magical step. I mean, I'll keep going, but when I cancel those out, I get the velocity on the outside squared is nothing more than the velocity on the inside plus the velocity of the train, and there's Pythagorean theorem. So why did it work?
So that is Pythagorean theorem. That's Pythagorean theorem for the velocities or speeds, if you're thinking just of the magnitude of the velocity. And so that's Pythagorean theorem for the velocities, written down as an equation. So you've got that, and that is just Newtonian physics. That is Newtonian physics. See what he's done, he's moved that over to that side, and doing that he's made it a plus. That is just Newtonian physics.
There, it's obvious, right? Pythagorean theorem's pretty easy. I can go through my mechanics, I can work it out. But what assumption did I just make? Well, time was not zero. Okay, but I agree time's not zero. It takes a while for it to go up. I have assumed in here that the times as observed by you and me are the same. I wonder why that would be true. Seems true. Well, yeah, right, it seems true. Well, that's good enough. And there's the problem. There's Einstein's genius. His genius falls in right here where he realizes that the whole reason this works is because the times by the inside and outside observers are the same. Let me make a small modification. here's Einstein's thinking here. And again, maybe I'll do it in red here, because this time right here was the time measured and calculated by the outside observer. This time was for the inside observer. Einstein realizes, and what I'm trying to show you is if those times are the same, then these speeds observed by the inside and the outside person have to be different. And so I see the ball going up at 30, you see it going at an angle of 50. And for all those centuries before Einstein, everybody was happy with this statement.
Happy with the statement that T out was the same as Tn, with the times are the same, and he's calling it assumption, but I would disagree that Newton's probably using it as a definition that those two things should be equal, and that's what his followers have taken. But now they're taking it as an assumption that those two things were equal in Newtonian physics. So that is the connection basically with Einstein's relativity. In Einstein's relativity, special relativity, he's going to assume those two things are different. But in Newton, you're going to have those two things the same. So that is the connection between Einstein and Newton in this maths. And now he's going to put in as the speed of light as being v out and vn, and he wants those to be the same value. And that would be the reason for why you're making these t out and the tn different. So carrying on.
But Einstein realizes that it is this assumption that the times being the same results in the addition of velocities using Pythagorean's theorem, which would give you different speeds. He goes back to the experiments and says, what if this, instead of being a baseball, is a beam of light? And so as it goes upward, the velocity as seen by the inside person is c. If the times are the same, and here's my main point, if the times are the same, there's no way the speed on the inside and the outside observer can be the same. Fair enough? And that's what science had been doing up until this point. What Einstein realized is something new is going on, something different, something we did not notice in the past. And what seems to be is that the speed of light is the same. So he takes this bold step and says, I am just going to assume, without explanation yet, just assume that the speed on the outside is also the speed of light. And so somebody in that train who shot...
Right, so Vn equals C and V out equals C. There's quite a lot I could complain about, but we're just taking it for the time being. That's what's going to happen. And when you're doing that, the time's going to be different. T out and T in are going to be different because you're doing that. So just accepting that's what he's doing, that he's making Vn equals C and V out equals C, and then so he's going to make T out and T in different.
Shines a flashlight up, they see it go up with the speed of light. Somebody else who's on the outside of the train also sees it go up the speed of light. Einstein's question is that possible? And what I want you to see is it could be possible if the times are different. And so are the times by a different observer actually different? Is the time observed by your clock different than the time observed by my clock? Now let's just assume that's true for a second. What would that mean? Well, here is the main step. If V on the outside is equal to C, and V on the inside is equal to C, then time by the outside observer cannot equal time by the inside observer.
So that's the connection, spelt out even more, the connection between Newton and Einstein. So basically from that equation, Newton would say T out is equal to T in. So you would be able to cancel that, and you would have the Pythagorean equation for the velocities as that. But Einstein is going to say V out equals C, V in equals C, and T out does not equal T in. So they wouldn't use that equation anymore. That equation is not used anymore, and T out and T in are different. So that's the connection between Einstein and Newton.
Our choice. We either can assume the times are the same and then the speeds can't be the same, or we can assume that the speeds are the same and therefore the times are different. And so let's take that bold step and replace the velocity.
So now he's going to put the put this into that equation up there. So he's going to work out what will be the time dilation equation.
On the outside with c squared, the velocity of the train with just v, since the other speeds all have a c in them. Then what Einstein notices.
So he was a bit late putting up the squaring this t out, but you get the idea. That is the equation. That's how that equation has been changed into that equation from the way Einstein wants to deal with it. And so that's the connection being further expanded upon. And from this you're going to get the time dilation equation. There's a lot I can complain about, but really all I want to concentrate at this stage is looking at the maths, and this is the maths, and this is the connection between Newton and Einstein.
Is right there. Different times for different observers. Let's see if we can work out how they're connected together. I think if you put the c squared over here, you'll see 1 minus v squared over c squared then would equal to the time on the outside.
In a sense, you can look upon this as divide this equation through by divide it through by c squared.
Squared equaling to time on the inside squared. If I take the square root, I get the square root of 1 minus v squared over c squared equals time on the outside divided by time on the inside. Oh, no square. I'll take one more step, which is the common way of writing it, although so far it might look a little bizarre to write it in the denominator because I did not have a fraction and now I do have a fraction. But it is standard practice then to refer to this ratio of v compared to the speed of light as beta. It is also common practice to refer to this 1 over the square root of 1 minus beta squared as gamma. And so this would become time on the outside is equal to gamma times time on the inside.
So that's the time dilation equation. It's going to make it a bit more confusing now because you're going to talk about proper time and non-proper time. But that's basically the equation.
Now again, let's pause here, because this is going to lead to all kinds of crazy consequences, which is what this chapter is about. Because we are now saying here that instead of assuming the times are the same, we are going to assume the speed of light is the same, which means the times are different.
And that's highlighting the difference between Newton and Einstein once again. From that equation, you can deal with that via Newton and you would have that the same as that, or you can deal with it from Einstein and you would have that as different to that. So that is the connection being highlighted once again.
Now, I'm sure most of you, or most of you who haven't seen this before, are probably going, wait a minute, I've had a watch. And I've used my watch, and it doesn't really matter if I was in my car or not. Don't tell me there's something different about time if I am moving. But wait a minute, let's look carefully here at the numbers. How fast was your car moving compared to the speed of light? Really, really slow. I mean, just for the sake of discussion, let's just say my car was moving 70 miles an hour. I take 70 miles an hour, I'll divide it by roughly 2.2, and that's about 32 meters a second. I'll take 32 meters per second and divide it by the speed of light. That's pretty small of itself, but this is asking me to do the square of that, okay? So I'll square that. And we're looking at 0.1 times 10 to the minus 14. So if I take 1 minus that small number and square root that, what do I get? I bet even on my calculator, if I go 1 minus that answer, I get 1. And so that's more decimal places than the 10 on my calculator can handle. And so what do I record in my car versus out of my car? A time that technically is different, but I would never notice it at 70 miles an hour. I would never notice it at 25,000 miles an hour. I wouldn't even begin to notice it till probably close to the speed of light. If you remember that little chart that was here, I put a dotted line.
Yeah, because the effect is very small. You don't notice it at very low speeds.
At about 10% the speed of light. So here's kind of our statement. Our statement is, nature could be working this way. We just never noticed it. We just never went fast enough. Now we're going, with these little experiments, fast enough. And maybe that's why Newtonian mechanics isn't working. We based all of our Newtonian mechanics on the assumption that the times by the observers were the same, and so the speeds were different. But perhaps that's not how the world works. Perhaps the world has the speed of light the same.
Well, I'm getting upset a bit about what he's saying here, but I really intended to let it pass. But what he's doing with the maths is he's making those two speeds the same, so then you can have those two things different. Well, if you were doing it by Newton, you would have those two speeds different, and then you would have those two times the same. So why can't you just carry on interpreting that equation by using the way Newton would do with it, rather than to do it with the way Einstein would deal with it, which would be that.
Something special about that, and time is different. Now, since we never noticed time was different, then there must not be too much change to time unless you get really, really fast. So in case you think this is too weird and too bizarre, yes, accurate experiments have been done. Yes, they have recorded time differences. Probably one of the most famous ones is just put an atomic clock on a passenger plane.
I'm letting it go about complaining about these experiments, but I would say the experiments are set for that. So if you're doing it by Newton, you wouldn't be setting it for that.
Fly it around the world. You put one clock on the tarmac, you put another on the plane, you fly around the world, you land again, and they differ by a few billionths of a second. Okay? Not much, but exactly in the amount that is accurately predicted and accurately calculated. And that's not the only experiments. Many other very famous experiments have been done because, again, this is a bold statement. You need some kind of experimental evidence if you're going to get people to buy in to say that the times aren't the same, because we live in a world where we go slow compared to the speed of light. We're not used to our clocks having different time frames. But they do. In fact, let's keep going. You'll notice I did not box this purposely because I want to make it look like your author has it. Your author, instead of calling it time on the outside, he calls it a delta t, meaning this is some kind of change in time, some kind of a lapse of time. Let me just make sure I use the same notation. Yeah. And then he puts the gamma here, and he calls this a delta t sub p, and this sub p is what we're going to refer to as proper time.
So, earlier, that would have been called T out, and that would have been called T in. So he's now going to call it proper time, and that is non-proper time.
Because here is the dilemma we're going to have to work through this whole rest of this chapter. If the times are different for each observer, how do I define time? If you said it took 1 second, does that mean it took 1 second for me? Your time and my time aren't the same. And they're not the same as that person's time over there. So we all get different times. Now on the surface that may sound like, oh, there's nothing we can do with time now, it's completely random. But that's not true either. There is a connection between all these times, and it's the relative speed between them. And so we still have a usefulness with time. It's just we need to remember there's no such thing as one time. It all seems to vary. And it's not just a perception. I know that, sometimes time can seem longer because you got to sit and listen to a 2-hour lecture and it seems like 3 hours, or it seems like a half hour, or the way Einstein put it when somebody asked.
Now he's going to talk about what Einstein says, and I particularly don't like this quote from Einstein, and it's got nothing to do with all of this math here. It's nothing to do with it. It's about subjective experience, where you have this feeling of time in yourself. It's nothing to do with looking at a clock. It's feeling within you that sometimes time seems to drag slowly. When you're bored, time seems to go slowly, and when you're having a good time, seems to go fast, and that's just subjective feelings. So I particularly don't like this quote, but here we go.
How are we supposed to understand this relative time? And he said, when you sit next to a pretty girl, time goes faster. And so he was unfortunately trying to give a emotional response or a perspective response, but that's not really what's going on. Everything.
As he noticed, he said there's not really what's going on. None of this maths has any connection to this feeling you have of time, and so tying it into that is kind of a non sequitur, no connection. But it does fool a lot of people. They do have this feeling that time, from their subjective point of view, goes at different rates. So when Einstein comes up with a theory where time does go at different rates, well, maybe he's right. It feels right. It's a feeling that it's right. But none of this maths has anything to do with that. So you've got to put that aside and just go with what's presented. what's presented is Einstein's going to have V out and V in as equal to C, and then T out and T in will be different.
Goes a little bit slower here. Let's look closely at this. This proper time then becomes our reference point. Everybody will agree with the same proper time. And so what do we mean here by proper time then? Well, I did it calling it the inside piece. Let me get away from it, but what was special about that inside piece? Well, the inside piece, there was, I'll say, no motion to me. Now, let me see if I can make that a little clearer. What my time was, as you guys watch and as I watch, here's the time, right? On the x-axis, I'll start with my flashlight right here. So if I was measuring the position of the light when it got started, I would say the light is maybe 20 centimeters away from me on the x-axis. The light beam goes up and hits the ceiling. Okay, on the x-axis, where is it? Same spot. And that's what I mean by no motion. So the person on the inside, the position of the event did not change. There was no motion for that one. But what about you? Right. And so you guys are in this room. Let's say you pick the origin to be the door. So when I start the flashlight, you say the light starts 3 meters away. But when it hits the ceiling, it's more than 3 meters from the door. It's now 4 or 5 or 6 meters, depending on how fast I was moving. Fair enough? So you are the non-proper time. You have moved. Somebody else could be even driving a car. They would be moving even faster than you, or slower, depending on which way the car was going compared to me. But that person, too, would record a non-proper time. Now, that non-proper time would be different than your proper time. Fair enough? Because the speed at which that car is moving relative to me is different than the speed you are moving relative to me. And so we have an infinite number of different times for this event to take place. We have only one proper time, and that's going to be our key to keeping our physics going. It's not just any random, useless time. This is an important one. And so if somebody's in the car or you are in this room, all of you can measure your time, do a calculation, and get my time, the proper time. And so we have now a reference place. And so this is going to be an important discussion, time. The hardest part of these homework problems really are looking at the problem and deciding, is it proper time or non-proper time?
So I can't resist making a comment now. He's given this lecture, his talk on relativity, and now he's got to test the students to make sure the students agree with what he's told them. And it's my point of view, it's a sort of brainwashing. So he believes in special relativity. He's told the students special relativity, and now here's your test, here's your homework, come back, tell me what your answers are, and I'll mark whether they're right or wrong. And so you've got to agree with him, basically. You've got to agree with what he's told you, or else you get marked wrong. And so that is a sort of like conditioning response. There's a famous thing about Pavlov's dogs, and they were conditioned to salivate whenever they had heard of something like a bell. And it's the same thing. You get a talk from somebody like this, and then you are conditioned to give the answers that this person wants you to give. And if you do as you're told, you get rewarded. And that's how it's done. You're conditioned to believe things that are wrong, But carrying on, we will now get to the contradiction.
Because calculating gamma is not real hard. I mean, let's face it. What are you going to do to get gamma? You're going to take the speed. You're going to divide it by the speed of light. You're going to subtract it from 1. You're going to take the square root. You're going to take the reciprocal, and you got gamma. The biggest question then would be, now that I have gamma and I have time for the event, how am I going to put it in here? Do I have the proper time or do I have the non-proper time? So there's lots of non-proper times and only one proper time. Oh.
So we have to bring up a point that all we're dealing with up to so far is just maths, really. It's just a bit of manipulation of maths. And so if you're doing maths this way, well, I'd raise a lot of protests, but it's just maths manipulation, and you're not getting to the bit where you are making the contradiction in the maths, and that's coming up in a minute. So letting it go, yeah, okay, you've messed up, you've manipulated the maths to be like this, and you haven't made any, I suppose, contradictions up to now, and you are going to add a contradiction now in a minute into the maths.
Let's even make a graph of gamma. If I plotted gamma versus the speed, and again, I'll put a solid line at the speed of light. I'll put a dotted line at 1, because if your speed was 0, what would you get for gamma? Wouldn't I get 1?
So if you remember what the equation was for gamma, when speed is 0, it's when the velocity equals 0, the speed of light is still c, and into that equation you get the value 1. That gamma gives the value 1, and so when its velocity is 0, that non-proper time is equal to that proper time. I won't say it once again. Non-proper time there is equal to that proper time there, and that's when gamma equals 1. I need to put the little dot there, and this axis is gamma, and along here is velocity, and that is the value c for the speed of light. So when v is equal to 0, which is there, and gamma equals 1, and proper time is then equal to non-proper time in that equation. Carrying on, just having to accept that. We haven't got to the contradiction just yet, it's just coming up soon.
And in fact, as your speed begins to increase, not much would happen right away. Because when you take your speed and divide it by a big number, it's small, you square it, it's even smaller. And so really, you're not going to see much of an effect with the gamma for a long time. Which is why proper time and non-proper time would be roughly the same number for any low speeds. That was the assumption that Newton and Galileo and everybody had done up to Einstein.
And that's false. He just told a lie. He's probably told it and not realised he's just lied. We have the connection between Einstein is Newton as V out and Vn equals C. V out there and Vn equals C. And then we have T out as not equal to Tn. That is not equal to that. And then we get the time dilation equation. But saying that is the connection between Newton and Einstein. He's gone through all that. But now saying the connection is about gamma, that is a lie. That is false. That is a contradiction. He's making a different connection between Newton and Einstein. I'll highlight it again. I'll go back to that a little bit because it happened very quickly. here we go again.
And non-proper time would be roughly the same number for any low speeds. That was the assumption.
See, he's saying that is the assumption, and it isn't. It is not true. That is false. That is a contradiction. You're making a different mathematical connection between Einstein and Newton. That is a contradiction in your maths. I'll go back to a bit earlier. Because it happened very quickly.
If your speed was 0, what would you get for gamma?
Gamma equals 1.
Wouldn't I get 1? And in fact, as your speed begins to increase, not much would happen right away. Because when you take your speed and divide it by a big number, it's small, you square it, it's even smaller. And so really, you're not going to see much of an effect with the gamma for a long time. Which is why proper time and non-proper...
So, he's talking about gamma. He's saying that for low speeds, gamma is approximately 1. And he's saying that's going to be the connection between Einstein and Newton, which is false. It goes against the connection he gave earlier.
Proper time would be roughly the same number for any low speeds. That was the assumption.
False. It wasn't. You didn't use that earlier. You didn't do that earlier.
That Newton and Galileo and everybody...
That's false. You're doing it different down here.
Everybody had done up to Einstein. But Einstein finally now has something to say, you know what?
So he's making exaggerating claims about Einstein, but you basically have it now. The gamma, he's using that gamma as the connection, and it's not. It's in contradiction to what he's done down here with the maths. So you've got two different bits of maths, that bit with the gamma and this bit here, and he's making two different claims of how Newton is connected to Einstein. That is a contradiction in the maths. And it's awful, terrible that they've done this. They assume that at low speeds, gamma is approximately equal to 1, and then you've got Newton's time as being an approximation from special relativity, when it's not. The connection between Einstein and Newton on time is V out equals V in is equal to C, and then you're taking T out is not equal to T in. That is the connection. So whatever speed you are going at, all you have to do is undo what he's done here. Undo saying V out equals C. No, undo saying V out is equal to V in. Have the value of V out being different to V in, and then set T out being the same as T in again. And that is the connection to Newton. By saying the connection to Newton is that for low speeds, gamma is approximately equal to 1, and then you've got Newton. That is a contradiction. That goes against what you're doing here. You can't have it both ways. Well, they do try to do it both ways. They like to say 1 equals 1 sometimes and 1 equals 2 sometimes. It's contradiction in the maths. They sometimes do the maths correctly in Einstein's relativity, and then they do sometimes do it wrong. So that's what's happening here. 1 minute you're alright, 1 minute you've gone through it all and you're okay, yeah, that's okay. As long as you're doing that, that's okay. Yeah, okay, that's okay as long as you're doing that. But then you get to the bit where you make the contradiction, where you say something else is happening. That is how they built up the connection between Einstein and Newton from that. And then saying it's something else instead, that is a contradiction. The maths is totally wrong from that. So there you have it. Einstein's relativity is nonsense. Its mass is messed up. And that's basically what you've got in these relativity textbooks. You have the maths messed up. You have how Newton is connected to Einstein as messed up. And as I pointed out, I think if you've got nonsense, you can't then test that nonsense by experiment, because whether you've done it, whatever experiment you do, you've still got nonsense. It never makes sense. You've got a theory that does not make sense because the maths is not correct. The math is messed up. You can't then do an experiment with that. It's just gone. Whatever they're saying about testing it by experiment, no matter how many times you're doing the experiment, it doesn't matter. If your math is messed up, all you're doing is putting your experiment to agree with messed up maths. And that is the nonsense they've got here. Go back to the beginning. Title is Maths Contradiction in Einstein's Relativity with its connection to Newton. And that's what they've done. Einstein, as I pointed out in some of my other videos, was no good at maths. So little math mistakes like this are things that he does. So, and they're supposed to have people check up on this, but no, you find out they've still carried on making that mistake. They've got the two different connections between Einstein and Newton, and that's why you've got this major problem now with, say, how would you connect quantum physics with Einstein's relativity? Well, Einstein's relativity, that maths, has contradictions in it. Sometimes you're saying from Einstein's relativity that 1 equals 1, but sometimes you're saying 1 equals 2, so it's a mess. That's why you can't connect the two things together. Einstein's relativity has all these mistakes in it. The maths has mistakes in it. The experiment doesn't show you that the math is messed up. You're supposed to look at the math and say, that is messed up maths. You can't do an experiment on this because the math is messed up. But they haven't clicked with that. We go back to him. He's given his lecture. He hasn't realised that he's messed up the maths. He's suddenly made a mistake. And he's probably been taught that mistake as well. They all teach it. So he's teaching this mistake to the students. They're sitting there. They've got to do their homework. He marks them whether they're right or wrong. So if they agree with him, then they've got to do it wrong. They've got to do this maths wrong. And then that's their belief in Einstein's relativity. Belief in Einstein's mess, basically. If you do the maths wrong, then you've got it. Thank you.